Okay, today I want to start with this picture I drew, and what it is basically a simple version how you might look at history of your repository. And this C1 C2 stands for commits. This is the first commit for our repository, the initial commit. Here is the second one, and we currently have our head pointing to C2 commit to, and for instance I drew here that our C2 points to some tree. Let's actually rename it to tree, the second tree, tree that is related to the second commit, and our tree currently is equal to index file because we don't have any changes in working directory, so we have index pointing to the same, having the same structure as T2 does. And this is what I want to start with. I want to create a repository and implement this kind of structure, this kind of tree. And maybe how we add these two files, maybe we previously already had some of the files, so let's do that. Let's copy these three, right? Let's remove this one and this one, and point our first commit with the same color to tree, the first tree, and maybe during this commit only a single file was added. So let's just to make it a little bit more clean, let's remove let's remove second file, because during our first commit we added a single file, and maybe it will be much easier if you do that, and rotate this line also, this arrow also. So here's our first tree, and our first commit points to the first tree, and first tree only contains a single file. Tree contains a blob of a single file, and the file is called 1.txt. And because during the second commit we won't change this file, we will only add let's make it a little bit clean for now. Maybe move these lines away for a second. So we have a second commit, and during this commit we added extra file T2 to our repository, and we haven't changed T1. So we haven't changed the first file, so our tree still has a reference to T1 commit. So you can draw, let's make it a little bit more accurate here. You can represent the structure of our repository during the second commit like so. We have a tree representing the second commit, and this tree is different from the first tree, and namely, Git will create another tree because we added during this commit we added another file, and the blob for this file will be the same on both trees. And during this moment, in this case, our index file, if we don't have any changes in working directory, will be equal to our tree2, just because index represents, if there is no changes in the repository, index represents whatever we have in working directory. So here's our picture. Let's remove these red lines for now. And for further demonstration, I will start implementing this structure in our repository, and then go from here, showing different visual using this picture to show visual references, what's actually going on, because I think that it's much more understandable what's going on in the repository if you have a picture of it. Anyway, let's start implementing our structure here, and we'll have this picture as a reference point. Let's go to our repository. Let's remove everything here and create another repository, another folder, cd into this folder, and initialize the repository here. And the first step will be to create a C1 commit, and we do it like so. We create 1.txt, and it doesn't matter what the content is. Let's just type file 1.txt content. We have our file. Now we need to create to commit it, adding it to staged. And what's going on right now, we have our index. Let's imagine that we don't have this part of our repository yet, and we don't have tree. We don't have actually the first commit. We have only let's say that now we have only file 1.txt, and we don't have any commits, so we have an empty repository. And in this case, we just, with command git add git status, we just added our file to staged. So it means that now index actually pointing to our file, like so, right? And but we still don't have any commits. Now when we run command git commit -m and specify, let's use C1 as a commit name, just for simplicity. We press enter here, and now we have a history. It means that we have one commit 1, and this commit 1 points to a tree. Let's actually only take a commit 1 for now. Here's our commit 1. This commit 1, and it points to some tree that was created for that exact commit, tree 1 that was created just now, and tree 1 is pointing to whatever index was pointing to before. I mean, index still points to T1. It means that Git will take everything that index is pointing to and make so that our T1 is pointing to the same things. So here is our structure right now. We have a our commit references T1, and T1 references 1.txt blob, and we can see it by actually getting the cat file commit output of our current commit. Here we go. Here is our T1 tree 1, and this is the message. And now we can inspect tree with git tree. Here's our T1 that 1.txt that T1 is pointing to, and also we can inspect our index file like so, and you see that index also points to the same to the same object. Namely, this is a blob object representing our 1.txt file, and you can check the file itself with git head file blob and provide a reference to the object. Here's our consent. So now what we want, let's move it to another area, to a more clean one. For instance, let's move it here, and now we want to add the second commit. Alright, let's take a file, for instance, and maybe to see it visually better, let's move this portion of our image to the right side, and we will go from left to right, and we need to point this arrow in different direction, like so. Our T1 is pointing to this file, and maybe let's move the file to the bottom, something like so, and our index file will be located somewhere here and point to the same files. Like so, and okay, let's remove it and recreate, and let's remove this arrow also, recreate. If we want to show the tree reference, we'll use the gray color, and for index we'll use another color. Let's say this one. Here we go. Now we want to commit another file to our directory, to our repository, namely yes, and I've also forgot about head, and head will be of color, of this color, purple color, head, and head has a now points to commit 1. Now let's move to the second file we're gonna add, and basically we can speed up the process by selecting all of these components and copy pasting them, and moving to let's actually first create it in our repository and then show it. So to create a second file, we first created file 2.txt content, then we add this file and commit it with message c2. So before we commit, let's display what we have. We have, well, we still don't have c2. We just have another file, and for now nothing actually points to this file. Actually, for demonstration purpose, let's move our index to the very bottom and rotate our line like so. It will be easier than to move index from the left to the right. Now we have T2, and our index already points to it because we added the file to staged area, and we can see it with a git ls files stage. Here we have 2 files, and this is the blob for the second one, and nothing else points to this file yet. And to make a new commit. You do it with git commit -m providing C2 message. Now we have a second commit, and let's show it in our picture. So from this state, we just created a new commit. We created a new file, a new tree. Let's rename our commit to commit2 and file to tree2. And this tree points to both of our files, like so, and like so. It reuses our second tree reuses the first file, first blob from the previous tree, and creates another blob for the second file, and these trees are different. Then I'll show you how an empty commit will look here, because you can create an empty commit that doesn't actually require a new tree in our repository. So we have this relation that our C2 commit points to C2, and we also have this relation, because C2 contains a parent's reference to C1, and C1 doesn't have a parent reference because this is the initial commit. So here's our structure, and also our tree was moved to, our head was moved to point to the second commit. And actually not only the head, so how can we do that? Because we don't actually have a head pointing to commits, we have a head pointing to a branch, right? So to show that, let's create a branch and use a green color for that. No, green is very bright. Let's use another green, like so. And also we use an arrow to show where master is pointing to. So here's our overall picture of our repository right now. Right? What next? And next, now that we have our structure and our picture representing the structure of this repository, let's try, let me show you several interesting features. First of all, I want to create an empty commit, and to create an empty commit, I'm gonna actually, let me first display it and then create it. There is a way for us to create empty commits, C3, and I just want to show how it will point to the same tree previous commit did. So this will be a simple commit, but without any changes. So Git doesn't need to recreate any objects, and this is why our third commit will point to the second tree. We'll have something like that. And to prove it, now let's switch to terminal and actually create an empty commit. And you do it with the command. Well, you just do git commit. If you now provide an option like C3 message, it won't allow you to do that. It will say, it's saying that there is no changes in the repository and you don't have this commit yet. So you need to provide an option allow empty, and this way our commit is created, and now we have our head pointing to the master and master points to this our empty commit, And if we describe our commit, it will point to this tree, right? And if we we can reference commit, and let's show where previous commit is referencing to, and then compare both of the trees. You can show commit with like so, with head. Here's our latest commit, and here's the parent of this commit. And as you can see, trees are the same. So here we go, and this is how an index still points to a previous commit, previous object of our tree tool. So now I want to also show you what's gonna to happen if we have several files with the same commit, with the same content. So I want to create a structure like so. I want to create file 3. Yeah, I think that how can I do that? So I want to show you that if you have several files with the same content, a tree will represent these files as a one blob, because blobs are just blobs include content of the file, and they're represented by a hash of this content. So if you have an equal content of the file, hash function will return the same value. So tree will point to the same blob for multiple files, even though the names of these files will be equal. So to show you that, let me try to first. We'll have something like that. We'll have commit 4, tree number 3. We also have this relation, and tree 3 still be referencing. How can I do that? Like so. Okay. Tree 3 will still be referencing 1.txt, and also 2.txt. Right? Like so. Like so, and still have to change this one, like so. And we're gonna add a third file, and third file will be equal to second file. And instead of pointing to a third file, our tree will actually use a previous reference, a previous blob, and our tree will contain several references to the same blob instead of actually creating a new blob for our text tree file. And to show that, maybe I can display an equal sign here, that we have two files with different names, and our tree 3 will point to a single blob, one reference in both of these files. And index will also will also do that. So we need to duplicate this arrow also, like so. And of course branch and head will also point to the new commit. So let's switch to the terminal and try to do that. We need to add file 3.txt. Actually, I don't remember the contents of the second one. Let's just copy second file to the third one, and content should be equal. Okay, now we're gonna add this file, commit it, name the commit 4, and now let's check what we have. First, let's check where head points to in terms of tree. Cut file, commit. Here's our this is a different one, because you can see previously it points to the previous commit pointed to a T2, and here's our index ID for T2, and new commit points to a new tree, and let's ls3 this new tree, and here we have 3 blobs, because we have we have 3 references, but only 2 different blobs, and as you can see file 2 and file 3 points to the same blob, and it's represented by 3 arrows here. 2 of them points to a single place, and the same picture if we check our index file. Same here. It's basic. These references are basically similar to what T3 has. So this is about pointing to the files with similar content. The next thing, I want to show you how you can, several things if you have multiple branches. To do that, let me quickly remove this one, and maybe let's imagine that we want to create this kind of structure, like so. And it will be a different branch. Oh, before before that, I want to show you another thing about branching. Let's imagine that we have this structure, and maybe we don't want to have our latest commit. We want we want to move our master to previous commit. Maybe we want to undo this commit number 4. So we want structure like so, right? And to do that, there is an option to reset our branch, reset hard, and we won't have this line also, because we won't have a third file. So we want to recreate this structure in our repository, and the command to reset branch to another commit is git reset hard, and you specify a commit that you want to your branch to point to, and in this case I will use annotation to find a parent of our latest commit. And now the last one is a third commit, and our tree become a previous one, a tree that head points to git ls tree head has only 2 files here, and same with git with index file, ls files stage. Here we have it. And the interesting thing about that is that if you create another commit from our current branch, this one might be called as a lost commit, because let's say we want to create another commit, and it will go somewhere here, and we'll have master and head pointing to it, and the name of this commit will be commit number 5. And it will point to as a parent, it will point to C3, and it will have a different tree structure. I won't show tree structures anymore here, because I think that you understand how trees worked, and there is a little reason to continue showing them. Actually, let me remove them to make everything more clear here, and all these lines also. Just move it somewhere here. These lines also, and this one. So we have this structure, and maybe let's make it a little bit bigger. And why it's interesting? Well, because you see, we cannot, we don't have anything that is referencing our C4 commit, because if you take a look at other commits, for example this one, you can go from master to this commit, because you can go to the parent of fifth commit, then so on and so forth, and you will end up in your C1 commit. But there is no way to go like to our first commit, right? You cannot, C3 commit doesn't know anything about C4, so you might name it a lost commit. Well, it still exists in the database, and you can reference it in several ways, but you know, this is a good way to basically remove a commit from the history if you want to go another direction from our C3 commit. And git reset is a tool to do that, to just move our master to points to another commit. And for you to understand, branches aren't something more than just a pointer to a commit. They branches doesn't have any more information, like, I don't know, some extra commits, or maybe you might think that a branch actually contains a set of commits. No, it doesn't work like so. Branch is basically a pointer to a commit, and a head actually doesn't point to commit. Usually head points to another branch, and head doesn't even know in this case anything about all our commits. It just points to the branch. So, and tags work similar. For instance, you can have a tag pointing to the second commit. And the interesting thing with tag, let's say tag 1, you cannot create a structure like so, because head cannot point to a tag. Thus, tag cannot move to the next commit or to other commits when you add another commit and head start to point to another commit. So tag cannot go with a development process as a master branch as the branches do. you add a new commit and you have this group of references moving with development process, but tags usually stay pointing to the same places. And this is good if you want to have like just a reference to a specific version. For instance, you have version 1.5, and let's change the color to something else. Usually you have kind of this color representing tag, and then you might have another version like 2.0, and they stay this way all the time, just for others to be able to download specific version of repository. And branches are usually used to point to development process line, because branches can go with head. Although there is an option, you see, if the head points to the branch, it's called a attached head, and you can detach head to point it to just to specific commit, for instance to this commit, to this one, like so. And in this case, head actually stores reference to specific commit, and if the file in special directory dir head will contain not a reference but actually an identifier of a commit, you are in detached mode, and it means that nothing like a branch or a tag will follow your head, and and there won't be any more references to commits that you will add that follows C2 other than a head. And when you switch back to the master branch, these commits that you just added, they might call you might call them as well as lost commits. So here's a thing about branches versus tags. So now let's restore the previous state. Okay, now what? We have talked about index, about trees. Now I want to show, let's create several more commits here. Commit number 5, commit number, I don't know, let's name these commits, because we'll have 2 branches, and this one will be called a new branch, so maybe it's a good idea to call this commit a new one, this one as a new 2 commit, etc. And here let's also copy this commit and rename it to master 1, master 2, and set an arrow here. So I want to create this structure in our repository. Here's our master branch, and we'll have another branch that will be called a new. Let's rotate this arrow like so and point it to our commit, and also rename this branch to new. Here's what I want to create in our repository. And why I want to create it? Well, I want to show you how different range operators work, like with 2 dots and with 3 dots, and what they will show you if you use them with git log and git diff, because it's very important to distinguish between these 4 different combinations when you use something like master, when you use something like diff, master, and new. What will it show? Or maybe with 3 dots, what will in this case it show? So to do that, let's recreate our commit structure here and continue from that time on, from that moment on. So let's return to our repository. We have 3 commits, so we have head pointing to commit numbers C3, a commit which with text C3. Now we haven't yet created a new branch. Let's add both of these commits at first, and I'm gonna create a file. Yeah, let's name our file m1.txt, right? File m1.txt content. Same with, and let's commit it. Name our commit m1, and another file m2.txt, file m2 content, and commit it as well before we need to add it. Add m2. Okay, here's our master branch ready, and with 2 commits. And now let's switch to C3 commit and create several commits in our new branch. And we can do that by creating a branch. Let me show you detached mode, how it looks. For instance, we use the same command git switch, but we need to provide detached mode, because you see, if we switch to previous commit like so, it won't allow us to, because switch expects a branch. It expects to work in attached mode by default. To switch to detached mode, you just specify a detached flag, and you can go back. I need to go back 2 commits, so I specify parent annotation 2 times, and fix a typo here. And now we are at C3 commit in this place. And now let's create a branch here, and here's a very here's optimization how you can create a branch with 1 command. You type git switch -c flag to create and switch to a branch, and you provide a name, new, and it should point to current commit. Here we have a log history with head pointing to a new, and we are at a 3rd commit. Now let's add both of our n1 and n2 commits. For that, I'm gonna create another files, n1.txt, file n1.txt content, committing it, add commit, and I said add n1, and now same with n2 txt, file n2 txt content, we are adding it, we're committing it, and 2. So here we have a structure equal to what we to what I showed over here. Now our head points to and1 commit, and one commit, like so, and I need another arrow here to point to several directions, and let's rotate this one. So we have a head pointing to a new. Now what? Now let's talk about range operators, and I'll start from log command, git log, and I want to show what git log shows us. If you, for example, type git log new, it will show us all the commits from our head pointing to a new to the very first file, C1. And this is understandable. You just want to show a log for your branch, right? Another option is to show a log for this range. And what this one does, let me show you in the picture. So first you take a master branch, right? And you basically, by this command, you wanna display all the commits that is equal to our new branch, and you don't want to show commits that are common with our master branch. So effectively, you just show commits from our new branch, and here is what double dot means. So we can view both our N1 and N2 commit. And now let's see what if we replace both of them with each other. We just do the same operation but for master branch. Both of our commits that are unique to master branch compared to, if we compare them to commits from just git log new, we have only 2 commits here for master branch. Anyway, this is about log with 2 dot notation. Now about 3 dot notation. And 3 dot notation, you can specify master and new, or in different sequence, new, master. It will show you the same thing. It will show you basically a sum of commits that are unique to master and it will sum up it with unique commits from new. In other words, it will take all the logs from the master branch, then it will take all the logs from the new branch, and it will only leave commits that are not shared between these 2 sets. So C3 is included in master log in all the commits that git log master shows. Same with new. C3 also included in this set. So C3 is the first commit that will be ignored, and we will end up with these 4 commits. And as you can see, we have N1 and 2, M2 and 1. Moving on. Now let's talk about div. Right? We have another command that that is very common when you use 2 and 3 dots notation. Div will show you the difference between 2 versions, two specified versions. Well, by default, if you just specify a master branch, it will show you the last commit and nothing else. Okay, now we have all these files just because we're currently on the new page, new branch. Yes, by default, if you specify only a single commit, git diff will compare current tree to whatever you specified. For instance, let's switch to this commit, like so, and see what git diff will show us. In this case, git switch detach. Remember we need to specify detach, and master, parents of the master. Now we are at M1 commit, and if we git diff with master, it will show us that to make state to transfer state from master to current state, we just need to remove this line from this file. Well, or in other words, we need to remove this file because this file doesn't contain any other lines. And this is what git diff will show you with a single argument. Now let's move back to, let's actually go to the master branch now, and see what git diff will show us with a range operator, with range notation. For instance, if we type git master, actually let's start with two dot notation. For instance, this form, we're taking a master and then we're comparing it to a new branch, and what it shows us, well, git will take the content of the master and will try to transform it to contents of a new branch, of a new, the latest version of a new branch, and it will basically shows us the same thing, how we can transform one state to another with minimum amounts of steps. And to actually create a new branch, represents a new branch from master state, you should remove both of these files, right? Because we don't need these commits, and you should add both of commits that are in N1 and N2 in a new branch, and this is basically what it represents. And same if you want to transform our new branch to the master. Same here, but in reversed order. Well, this is understandable. Let's move on to three dot notation, and this one, master, new. In this case, three dot notation only shows us a unique difference of our branch, of specified branch, compared to a new branch. So this command will find a nearest common ancestor of both branches, and we'll use it as a base point to gather all the commits from the master branch, in this case. So we need from master to new. I think that in this case it will show us a unique difference of N1 plus N2 commits. Let's try it. Here we have it. We only have a difference from N1 summed up with N2, and if we specify it in difference order from new to master, okay, we expect to see exactly that. Unique changes from the master branch compared to the base commit, where base commit is the first common ancestor of both branches. I hope that with this demonstration it's more easy to understand and grasp. So this is that's it about ranges in lock and div commands. What else can I show you? Well, let's imagine that we have this structure, we have a new branch, and let's imagine that we created our new branch to add some new feature from our master, and now maybe we want to pull all the changes from the master. And there is a way to do that. There are several ways to do that, and basically what we want to do, well, the first way is to merge a master to a new branch, and it will look like so. We'll have another commit here, commit m1. It stands for merge commit, and it will point to both of the parents, namely to n1. Let's change the color. It will point at the first parent, it will point for example to n1, and as a second parent to m2. And it will also, this merge operation will also move our branch head to m1, something like that. This is one way, and next we can go back and continue working on our feature, like so. And like so, right? But there is another way to do that, and to show you, maybe I'm gonna create another copy of this structure to then just to compare them. Let's make it bigger. So the interesting part is this one. We don't care about what was previously. So the other way you can go, if you want to pull all the changes, you can change where your commit has a base commit. So you can do something like so. You have a master branch. You previously point new to C3 commit, but now when our master actually grows a little bit, you want your branch to get all these changes from the master. So you want to have your line of commits clean of any merges, any merge commits, and you can do that by re-referencing your base commit. And basically what it means is you take your first commit and you actually apply all of your commits to the head of the master, and this way you have a clean history without any merges. You don't need that. You can go straight from n2 to n3, right? And this is called rebase, and what it does is it saves your current unique commits to a special place, right? All these commits. Then it moves a new branch head to whatever place you specify, in this case a master head, and then it reapply all your commits to a new branch. So this is the way, one way of several to actually pull changes from the master. The first one being merge, but we have already talked about merges. And but maybe if you don't want these merge commits in your branch, you can go with rebase. And how rebase, and how we can apply to our repository his steps to do that. Now we are located in in the master, let's switch back to a new git switch new, and now we type git rebase -int for interactive mode, and you specify a master branch. And okay, now what? We have two commits here. We don't want them. We can go with squish option to maybe connect them to a single commit, and there are a lot of other commands, but we don't care about them right now. We just want to create this picture. So we save our files. We don't want to do anything with our commits. One thing that we can do is rename, for example. Anyway, here's our operation, rebase operation. And now if we take git log, as I said, we have sequence of commits from C3 as our base, as our previous base. Now our base commit is M2, and yeah, and then we have N1 and N2 commits. So this is exactly the structure that we just showed here. And to prove it, here's our files from M1 and M2. Here's our files M1, M2, and N1 and 2. So basically, we just did exactly what I displayed. So this is about rebase. And you can use rebase another way to use a rebase, useful way. For example, you have these 3 commits, but you don't want to have 3 commits. You want to have a single commit, and to do that, well, there are several reasons why you might need it, but to do that, you can use the same git rebase operator to specify the first commit in your range that you want to change. In our case, we want instead of 3 commits, we want to have a single commit that will include all the changes from second and third commits. To do that, you type git rebase, and it will work the same way. It will it will move our base commit, and it will point it to the same place. So we don't want to actually pull changes. We just want to make all these operations that we can in the editor. So we specify. Let me show you what I mean. We specify the commit N1, namely N1 commit, git log. Here's our N1 commit. Maybe let's go with M2 commit, because we want to actually have both of these commits as a single one, and to do that we need to point to the base. Then git will do the same operation as previously. It will take all the commits after the base. It will store it in somewhere outside of our history, and it won't reset the branch. Well, it will reset our new branch to M2 actually, right? And then it will apply our changes to a branch new. So branch will point to our new N1 commit. At the same time, with the help of the editor, you will be able to squash all your 3 commits into one. So here's how it looks. You take your N1 commit and you specify git rebase, and I always use interactive mode just because it's easier to use it. So we need to take a base commit, specify it here, and here's our N1 and N2, and you have an option to squish them. We can just remove them to leave only a single commit, but we need to squash them. Squash, and we'll leave this peek command as it is right now, because we want our N1 to be a base of our composed commit. So now we exit the editor and change the name of our commit to only includes N1. So now, as you can see, we have M1 commit, which is actually a master, and then a single N1 commit, which is our new branch. So we get the same picture we have here. So this is it about Git base. So today we have talked about indexes, how they point to different blobs and to different trees. Then we talked about the difference between branches, detached and attached mode of the head. And also I mentioned how Git reuses a file structure if it wasn't changed. And what else? I also showed you a diff operator with range, diff command with range operator, and also a reset command to move a branch to another location. So I think that that's it for now. Yeah, that's it for now, and see you in the next video. Bye.